E-flow science and practice are about conserving or restoring the components of a flow regime that support desired ecological processes and related ecosystem services. In the first lecture of this unit, you learned about the processes generating flows in rivers and streams, and now we'd like to consider the variability of the resulting flow regime in time and space. Hydrographs are the most basic expression of the variation in flow of a river over time, so we'll begin with what they are and how they're measured. We'll then look at how flow regimes vary depending on regional characteristics or position in larger river basins. Finally, we'll consider how ecologically relevant components of hydrographs can be quantified. This information is an essential input to best practice approaches to e-flows. A hydrograph is a graph of stage or discharge versus time for a particular point on a river or stream. Stage is a measure of the level of water in a river measured in centimeters or some other unit of length. Stage is an ecologically important measure of the status of a river because both depth and wetted width are primary determinants of habitat in a river or stream. So knowing how depth and width vary with time and location is useful to determining how habitats vary with time. The graph on the left plots the variation in stage over a 24-hour period at a given point. This clearly delineates a very short-term pulse of higher flow passing the measurement point or gauging station in response to a brief rainstorm. This level of detail is possible when water levels are measured on a sub-hourly basis. The hydrograph in the middle records a high flow pulse of similar duration, but the magnitude of this pulse is expressed as discharge, or a volume of water flowing past the gauging station per unit of time, usually per second. For water management purposes, information about discharge is generally preferred over information only about stage, because discharge also includes information about flow velocity, which is another primary determinant of ecological habitats. Discharge also reflects the volume of water available for different uses, and is thus of greater interest to water managers. Stage and discharge are of course related, as shown in the graph on the right. The relationship between stage and discharge is nonlinear, with discharge increasing exponentially as stage increases. The curve describing the relationship between these variables is called a rating curve. Hydrologists devote considerable effort to constructing and maintaining rating curves for each of their river gauging locations because the unit most commonly measured is stage, but the preferred unit for management purposes is discharge. Stage is most commonly measured because it's easiest and least expensive to measure. It can also be measured quite accurately. The image on the left shows a standard best practice gauging setup where stage is measured automatically in a stilling well connected by intake pipe to an adjacent river channel. As the name implies, a stilling well helps to still the water level, erasing non-flow related variations in water level caused by short-term disturbances in the river like the wake of a passing boat. This is especially important when the measurement is made automatically, without the discretion of a human observer who would logically wait until the boat had passed before taking the reading. The upper photo on the right shows a stilling well of the U.S. Geological Survey adjacent to a river being gauged. Automatic measurements are stored on a data logger and either transmitted telemetrically to water authorities or collected from time to time by field technicians. Another common visual aid for measuring stage is the staff gauge shown in the photo on the lower right. Staff gauges are usually read by human observers who note the water level at least twice per day. Observations may be recorded in notebooks for future uploading to databases, but observations are increasingly input directly to databases using internet-connected devices such as smartphones or tablets. Any relevant observations of conditions at the site or problems with the equipment can also be noted at the time of observation. Measurements of discharge require surveying the cross-sectional profile of the river channel at the gauging point and measurements of flow velocity across this profile. In the equation shown on the slide, discharge Q is equal to the velocity U multiplied by cross-sectional area A. To increase the accuracy of discharge measured manually, the cross-section is subdivided into individual cells, each with a measured cross-sectional area. These are labeled 1 through 9 in the example on the screen. Hydrologists measure velocity in each of the cells, and the full discharge of the cross-section is found by summing the discharge of the individual cells. Velocity is measured with a velocity meter, either by wading across a small stream, as shown in the photo on the lower right, or by deploying the meter from a boat, bridge, or suspension system, as shown in the photo on the lower left. Today, discharge is increasingly measured using an acoustic Doppler current profiler, or ADCP. These instruments make use of sound waves and the Doppler effect to measure flow velocities across the river profile. I've included a video in the additional resources of the unit to show how these systems work. If you're not familiar with the Doppler effect, enter it into YouTube and you'll find many instructional videos about it. I've written it in the graphic on the lower right. ADCPs are also able to measure the cross-section, so they quantify discharge in real time. They've truly revolutionized river discharge measurements. Hydrologists make an effort to measure discharge across the full range of flow conditions in any river, from lowest to highest flow. Each time discharge is measured, they also measure stage. With these two data points, they're able to construct the rating curve shown in the first slide, which allows them to accurately convert hourly or daily stage data to discharge. Even when this relationship has been established, best practice calls for continued discharge measurements at monthly or quarterly intervals to ensure that the rating curve remains updated and valid. With a well-rated and operational gauging station, hydrologists can collect data on magnitude, duration, frequency, timing, and rate of change of flow, extending over days, seasons, years, and ideally decades. The hydrograph in the figure shows the 1974 summer flow regime of Holiday Creek, Virginia. Also plotted are the time and magnitude of rainfall events during that summer. The stream drains a small catchment of just 22 square kilometers, so there's a close relationship between flow and rainfall. Flows rise and fall in response to the runoff processes you learned about in the previous lecture. Flood flows occur in peaks related to individual rainfall events, while base flows between rainfall events are maintained by groundwater. Organisms in the river are adapted to these summer variations in flow and will make use of habitats that are created. The U.S. Geological Survey has continuously monitored Holiday Creek for 51 years and makes all data available free of charge over the internet. Here I've plotted the summer discharge of Holiday Creek from the year 2017. We see the same pattern of flood and base flows, but there's also a declining trend in base flow over this summer. The orange triangles present the median value of flow for each day over the 51-year record. 2017 flow levels appear low compared to the median. Long-term data such as these provide the water manager with valuable information to understand conditions in the stream and inform management decisions. Also note the discharge measurements made in June and August. Data for this plot clearly come from stage measurements converted to discharge using a rating curve. The two discharge measurements will be used to check that the rating curve is still valid. As you also learned in Unit 2, flow regimes vary as a function of catchment area, climate, geology, topography, soils, and vegetation cover. The three hydrographs on this slide depict three common patterns. Poplar Creek in Tennessee is a perennial stream flowing year-round. This is a humid area receiving an average of 1,400 millimeters of rainfall per year, but there is no pronounced wet or dry season in the long-term record. In contrast, the Frio River in Texas drains a dry area, receiving on average only 600 millimeters of rainfall per year and concentrated during particular times of the year. This leads to intermittent flow in the Frio River because the base flow component is missing. Dry conditions are stressful for stream organisms, but it is a natural condition that they're adapted to and that may even give them advantages over potential invasive species. The Little Blackfoot River is in a mountain area. The town of Garrison, Montana receives only 330 millimeters of rainfall per year, but it receives 1,450 millimeters of snowfall. This is sufficient precipitation to support perennial flow in the river, but there is a clear and extended peak in flow during the spring when snow accumulated over the winter melts. Many other patterns in hydrograph characteristics are possible, each representing another version of the natural flow regime. In the next lecture, we'll look at approaches to group and classify rivers according to patterns in their flow regimes. This classification is important in the regionalization of e-flow recommendations. In larger river basins, downstream hydrographs are increasingly influenced by the integration of upstream tributary flows, which may vary on short timescales as pockets or bands of rainfall move across the basin. This map is of the 38,000 square kilometer Potomac River Basin, located on the east coast of the USA. In the next slide, we're going to look at hydrographs from these three rivers in the basin. The South River is a small headwater tributary flowing into the Shenandoah River. The Shenandoah is itself a tributary of the Potomac River, which flows to the ocean. Keep this configuration in mind as you consider the hydrographs on the next slide. The upper plot on the right shows the hydrographs of the three rivers over the same roughly 2-week period that included rainfall that was most intense in the headwater area drained by the South River. Note the greatly increasing magnitude of downstream flow as the Shenandoah and Potomac concentrate the flow of multiple tributaries. Note as well the delay in the downstream progression of the flood wave, which is partially due to the distance traveled, but also to the retention of the upstream channels and potentially floodplains. A different quantification of the flood wave is shown in the plot B, where discharge is normalized or standardized by the area of the catchment drained. This emphasizes the high level of discharge per square kilometer of catchment in the South River, where the rainfall was concentrated. This normalized flow decreases downstream as the Shenandoah and Potomac integrate the flood flow of the South River with discharges from other rivers that are not in flood. Imagine the complexity of these flow interactions playing out across the entire river basin over many seasons and years. Imagine, too, the communities of plants and animals that have evolved to take advantage of the predictable trends in flow variability and to cope with the extremes. Measuring flows across the basin enables us to quantify the nature and range of variability in each river and also to examine their interactions. These patterns of flow variability compose the natural flow regime. In 1996, at roughly the same time the natural flow paradigm was published, Brian Richter and colleagues at the Nature Conservancy developed a method to statistically characterize the annual hydrologic variation of rivers and streams. Their approach is called Indicators of Hydrologic Alteration, or IHA. It quantifies 33 parameters describing annual variability in the magnitude, duration, timing, frequency, and rate of change of flow. You'll remember from Unit 2 that these are the ecologically relevant characteristics of flow regimes. The parameters are organized into 5 groups. Group 1 includes mean or median values of the magnitude of monthly flows. Group 2 includes average maxima and minima of flows over different durations ranging from 1 to 90 days, number of days with zero flow, and base flow index, which is the 7-day minimum flow divided by the mean flow for the year. Group 3 specifies the timing of the 1-day maximum and minimum flows in the year. Group 4 includes the number of high and low flow pulses each year, along with their mean duration. And finally, Group 5 includes measures of the mean rates and number of rises and falls in the annual hydrograph. In addition to statistics to characterize annual variability in flow regimes, IHA also distinguishes and characterizes 5 ecologically relevant environmental flow components: extreme low flows, high flow pulses, small floods, and large floods. Thresholds are set to assign days in the discharge database to different flow components, and then data in each component are analyzed to determine 34 different parameters. Thresholds can be adjusted by the analyst based on knowledge of the river being studied, but default thresholds are also provided as a starting point. Considering these default thresholds, discharge values for days with flow levels below 10% of the mean daily flow for the period of record are classified as extreme low flows. Discharge values between 10% and 50% of the mean daily flow are classified as low flows. Discharge values between 50% and 75% of the mean daily flow of the period of record may be classified either as low flows or high flow pulses, depending on the rate of change in flow magnitudes from one day to another. If flow magnitudes increase by 25% or more between 2 days, a period of high flow pulse is designated and subsequent values are classified as high flow pulses. This condition continues until the rate of falling water slows to 10% change or less between 2 days. All discharge values higher than 75% of the mean daily flow of the period of record are classified as high flow pulses. Small floods and large floods are assigned to discharge magnitudes with a recurrence interval of 2 years and 10 years, respectively. Once assigned to the individual environmental flow components, the statistics presented in the green graphic to the right are calculated. This results in a total of 34 parameters. Applying the IHA methodology to hydrographs before and after the construction of a dam or other major impact to flow regime allows for a detailed analysis of how ecologically relevant flow characteristics have changed. These examples are from Lee's Ferry, which is just downstream of Glen Canyon Dam on the Colorado River. The dam was completed in 1966. The green line in the plot shows the annual variability in the selected parameter before dam construction, and the red line shows the variability following construction. The dashed line shows the median value, and the lower and upper solid lines mark the values of the 25th and 75th percentiles, respectively. The plot on the left shows the decline in the 30-day maximum flow following dam construction. The plot on the right shows the increase in the frequency of extreme low flows. These plots show the change in monthly median flows on the left and the change in environmental flow components on the right. We see that the natural pattern of low monthly median flows from August to March and high monthly median flows from April through July has been replaced by more or less uniform monthly median values year-round. This is a common form of alteration linked to dams operated for hydropower generation. We can anticipate that there have been ecological consequences both from the increase in natural low flows as well as the loss of high flows. The plot on the right shows the disappearance of natural large floods after the construction of the dam and a severe reduction in the number of small floods. What were naturally high-flow pulses become dominant after dam construction, with serious reductions in low flows and extreme low flows as well. While this sounds like an improvement in flow for those who see little value in low or extreme low flows, these may actually play important ecological roles in river and riparian ecosystems, as we'll see in a couple of units. The Nature Conservancy has also produced software to aid in analyzing hydrographs using the IHA method. I've provided you with a link to the site where you can download the software. Please download and install the IHA software on your computer. Also download the tutorial. As an exercise this week, you should go through the tutorial, which will take you through the process of importing hydrological data, creating a project, and creating an analysis of differences in the hydrograph of a river before and after a dam is constructed. After running the analysis, you will be able to observe outputs for all of the parameters I've presented in this lecture. The case for the tutorial is the hydrograph of the Roanoke River in the USA before and after the construction of the John H. Kerr Dam and Reservoir. Construction was completed on the dam in 1951, and filling of the reservoir began in 1952. Flow records for the Roanoke River extend back to January of 1912 and continue until September 2004. The dam was constructed for the purposes of flood control, hydropower, and recreation. It's operated by the U.S. Army Corps of Engineers. For the past 20 years, there have been efforts to change the operation of the dam to release a more natural flow regime downstream. The Nature Conservancy has been an active participant in this effort, and in just the past couple of years, it was agreed to change the operation of the dam so that the volume of water released from the dam each week is related to the natural volume of water flowing into the reservoir from unregulated upstream tributaries. This change in operation represents a great step forward in returning a more natural flow regime to downstream portions of the river. So, you now know that hydrographs are a graphical representation of the flow regime of a river or stream, expressing magnitude, duration, frequency, timing, and rate of change of flow for different points along a river over predefined time periods. The flow regimes expressed in hydrographs vary naturally depending on catchment area, climate, geology, topography, soils, and vegetation cover. They may be altered by many means, but the most rapid and significant changes are usually associated with the construction and operation of dams. Methods such as the indicators of hydrologic alteration provide a means to statistically characterize ecologically relevant components of flow regimes and also quantify the changes in these components brought by flow alteration. This information about natural and altered flow regimes is an essential input to eFlow's assessments. That's the end of this lecture. Thank you very much.